Hello everyone, welcome to Power System classes. So in the last class, we were looking at the general introduction about the power system. So in this class, actually we are going into the exact power system thing. So we will be starting with one. Okay. So we will be starting with power system. So we will be starting with transmission systems. So we'll be looking at transmission line. Okay. So what are the different types of transmission line, and what are the electrical characteristics of transmission line? So these two things are actually we are looking at this particular session. We can actually go forward. Okay. So in the last class, I have explained you what are the basic systems in a power system. Okay. So if you draw a a tower, I think you draw a tower. So these things are known as the insulators. Okay. And this will be the transmission line, and this tower will be actually in the ground. Okay. So the ground basically means this is a conducting connections, right? So the ground will be actually reaching here. This is the nearest grounded point. Okay. So this is the nearest grounded point. So, and this will be the transmission line. Okay. And if a current actually flows through this, so what are the use of these insulators? Okay. Why we need an insulator? So the why we need an insulator is that there are two uses of insulator. The first one is we use an insulator for mechanical support. Insulator for mechanical support. Okay. So insulator is used for a mechanical support. Then we use insulator which actually insulates our voltage from the ground. Okay. Which insulates voltage from the ground. Like in the sense, if there was no insulator, then this will be touching each other, and there will be single line to ground fault will be there. So this particular insulator has two purposes. First one is the mechanical support, because the line has to be supported right somewhere, because it cannot just flow through the air like this way. So this will be supported at this particular point through a string of insulators. So this is known as string of insulators. String of insulators. Okay. Because there are more than one number of insulators there, so that's why we are calling it as a string of insulators. Actually, from the number of these insulators, we can guess what is the the voltage of transmission. Like if there is something like a thumb rule is there, each insulator is assumed to be 11 kV or 1.1 kV or 11 kV. Then multiply with each insulator, we will get the what is the voltage actually transmitted through the line. Okay. I really forget what is the exact rating of one insulator. It depends on the insulator also. So insulator can be either porcelain, clay or something. There are actually new insulators are coming that are basically synthetic insulators. That is polymeric. Okay. You can see most of these are basically the red kind of a thing what you see, and these are almost white color. Okay. So these are basically different kinds of insulators, and we will be actually studying the design of insulators and other things in the coming session. So we will be actually concentrating more on the transmission line now. Okay. So there is a there are two types of currents which are flowing through this particular transmission line, or we can say the system. First is the conductive current. Okay. Conductive current. So the conductive current actually travels through this particular insulator. Okay. And there is another current. So there is another current which actually creeps through this insulator. Okay. the sense like this. Okay. This is a this is basically a leakage current. Okay. So if I draw the surface of the insulator, like this. Okay, assume this is surface of the insulator. So there will be a current. I will draw it another color. There will be a current actually flows through this particular surface. Okay. Like this. So you know that you already know that this is basically an insulator, right? So no current can actually travel through the bulk, right? Only the surface. Because why there is a current flow through the surface is that there will be surface contaminations. Okay. There will be surface contaminations. So surface contamination in the sense, if there are some kind of water, if the rainy season is actually happening, then there will be some kind of a water droplets actually happening here, right? So that means now if there is something like a conductive thing in the water, then the water actually starts conducting, some kind of a conductive material which is happening. Then actually there are something like a bird dropping. If there is a bird droppings are there on the top, and then there will be this creepage current will be there. Okay. So this length of the insulator through which actually the current actually travels is known as the creepage length. Known as the creepage length. Creepage length. So each set of insulator is having a this is something known as a creepage length. Okay. So this is because you have to remember here this creeping current or the surface current does not flow through the bulk of the insulator, flows through the surface of the insulator. Okay. So this is how we are saying it's a creepage current or creepage length or leakage current. Okay. It's also known as a leakage current. This is not the conductive current. So conductive current is actually flowing through the this transmission line. Through the transmission line. Okay. So I hope you understood what is actually why we need an insulator and what is the creepage length of the insulator. Okay. So these two things are really important. They will ask in the interviews what is basically an insulator, why we need an insulator, what is insulator made up of, what is the applications of insulator, and all these things you should read. Generally you will understand what is actually. Okay. So there is something known as a level of insulation. Okay. So for each system, there is something known as a level of insulation. So how much insulation we should provide in a in a transmission system or a distribution system? So known as a level of insulation. Okay. So if you take a tower, if you take a tower, the important property, important characteristics of a tower is that so the tower is always exposed. Okay, in the sense it is always the tower will be in the thin layer. Okay, because we cannot actually protect all the tower cannot actually keep all the tower inside something, right? Because tower is actually kept outside. So there is a high chance that there will be something known as a lightning strike happening on the tower. Okay. So if you look at the tower, there is something known as a wire which is on the top of the tower. That is exactly grounded. Okay, that is exactly connected to the tower. So this tower is basically this is for actually for protecting a lightning protection, for giving a lightning protection. Okay, because lightning strike will actually happening on the highest line. Okay, so the highest line is actually on the line which is above the tower. Okay, this is known as the lightning protection. Okay, so this is always grounded. So if a lightning comes here, it will split into two parts. One it will go here, and other it will go here, and through this will actually go to ground. Okay. So this is how the lightning strike happening on a tower. So below below 345 kV, comma, the insulation of this system. If a system is below 345 kV, the insulation of the system is decided by lightning impulse, okay, lightning response or lightning hour voltage. That is at this level below 345 kV, the insulation coordination or the insulation design is actually detected by or actually decided by the lightning hour voltage. Okay, they have to look at the lightning, how much lightning hour voltage is coming, and then we have to look at the design of the insulation. Above 345, sorry, above 345, above 345 kV, we have to look at the switching hour voltage. This is very important. Okay. So which hour voltage decides the design of a insulator. Okay. So if the system is below 345 kV, the insulation is decided by lightning hour voltage, and if it is above 340 kV, it is decided by the switching hour voltage. Okay. So what is basically switching hour voltage means? If you actually connect some kind of a switch or something, or if you disconnect a switch, then there will be something like an arc happening between these two terminals, right? So this can cause a switching hour voltage, or discharge of a capacitor. All this can actually create a switching hour voltage, because the problem is that this switching hour voltage depends upon the voltage of that particular system. So in above 345 kV, there will be the voltage of the system is very high. So the switching hour voltage will be very, very high, which is higher than the lightning hour voltage. So that's why above this particular rating, we have to consider switching hour voltage. That is the deciding factor for the insulation coordination. So these two numbers you have to remember these two numbers. Okay. So you should remember these two numbers. Why we are actually considering lightning hour voltage, switching hour voltage. If you consider hour voltages, there are different kinds of hour voltages. Like there is lightning hour voltage. First one is lightning hour voltage. Second one is switching hour voltage. Okay. This is lightning hour voltage, the first one. This is second one is a switching hour voltage. Then third one is VFTOs. That is very fast transient hour voltages. Okay. Then these are the things which is happening due to a partial discharge or something. So VFTOs will get there. That will be in very high frequency range. Okay. So this is very fast transient hour voltages. Okay. Then there will be damped there will be power frequency hour voltages. That is 50 hertz voltage. So the voltage will be in 50 hertz, but the magnitude will be very high. So something like single line to ground fault is happening. Then very high current, magnitude current, three-phase system. Then very high magnitude current with 50 hertz will be actually flowing through the ground. So this is something like very important. You should remember when you are going for an interview or something. So what are the different types of hour voltages? There are lightning hour voltage is there, switching hour voltage is there, VFTO is there, then power frequency hour voltage is there. Okay. So these things you have to remember. Okay. So you can just you can write these things in a book or something. So you should remember, you can remember all these things. Okay. So I hope you understand what is the insulation. And in the next class, we will be actually looking about the string of insulator, and the insulation, different strings of insulation. Then we will be looking at the sag and all the things related to transmission system. So today we will be looking mostly on the electrical characteristics of the transmission system. Okay. Okay. Now we can look at the classification of transmission system. Right. Classification of transmission system. So what are the different classifications? So first is based on the voltage level. So what are the different classifications according to voltage level? So the first one is normal transmission line that which actually see in our livelihood, near to your home. Okay, so I am not talking about that. Then we are actually worrying more about the transmission, not about the distribution. The first one is high voltage transmission system, high voltage transmission line. Second one is extra high voltage transmission line. Third one is modern extra high voltage. See, and fourth one ultra high voltage transmission. Okay, these are the four important transmission systems. So this will be in 11 kV or 33 kV. This will be in 66 kV or 132 kV or 220 kV. Okay, and this will be in 400 kV, and this will be in 765 kV. Okay, so if it is in the range of 765 kV, then it will be ultra high voltage. Okay, so if it is in 400 kV range, that is in modern extra high voltage. Then extra high voltage is 66, 132, 220. These levels are extra high voltage, and high voltage is 11 kV per 33. Okay, so these are the different classification according to voltage level. Okay, the next classification is more important for us. So you can just write down this. I will pause for a second. If you want, you can actually write down all these things. Okay. So next classification is based on types of conductors. So what are the different types of conductors which can be used for a transmission system? So that is, first one is, just remember all these names because they might ask you in the interview. Single strand conductor, and second one stranded conductor. First one is single strand, standard means multi-strand. Okay. Then third one is, I will write here, composite stranded conductor. Having more than different types of composite stranded. And fourth one is the bundled conductor. Okay. So these are the important types of conductors what we are actually normally using. So this is actually classification of transmission line, not exactly transmission system. Okay. So just note down these four lines because someone asks you what are different types of lines what we are using. So single strand conductor, then standard conductor, composite standard conductor, and bundled conductor. Okay. So there are some advantages of bundled conductor like having a different something known as the GMR, okay, geometric mean radius, so that will be you can see. I will explain you that because there will be less corona in a bundled conductor. That is the most important part. Corona is less here. Okay. I will teach you corona tomorrow, next class. Corona is actually less here. Okay, so that's most important part. Okay, so this is the classification according to conductors. Next is the classification according to length. Okay. So types of line. So according to length, we can actually classify these into three. The first one is known as a short transmission line. The short transmission line. So second one is known as a medium transmission. And third one is known as a long transmission. Okay. So these are the three important types of classification according to distance. Okay. So distance for short transmission line should be less than 80 kilometers. Okay. For this is known as a short transmission line. So only R and C is considered. Sorry, R and L is considered. Okay. Resistance and inductance will be considered here. Then this will be greater than 80 kilometer. Medium transmission line will be greater than 80 kilometer and less than 250 kilometer. Some textbook you can see it as 200 kilometer and some textbook is 250. So here we will take R, L and C. Okay. So long transmission line is actually greater than 250 kilometer. Okay. So if this distance is also already frequency dependent. Okay. This distance is basically frequency dependent. So this 80 kilometer and 250 kilometer are basically for 50 hertz. Okay. So if you think like this way, then for short transmission line, F into L should be less than 4000, right? 50 into 80 should be less than 4000. For medium transmission line, F into L should be greater than 4000, and commonly we are saying 10,000. Okay, so that is basically 200 kilometer. So less than 10,000, or in this case it will be 12,500. Okay, so in this 250 if you consider, and long transmission line, F into L, frequency into length, should be greater than 12,500. Okay. So in the question, if they ask something like for a transmission system of frequency 100 hertz, then they are actually considering some length of 500. Okay, sorry, 50 kilometer. Then is it a short or medium transmission line? Then you have to multiply this. So 100 into 50 is basically 5,000. So 5,000 is F into N. Okay. So F into L is greater than 4,000. So this is basically a medium transmission line. Okay. This is basically a medium transmission line. So these kind of questions are very important for one word questions. So you should remember this. So normally it is less than 80 kilometer, people will write it as short transmission line, but that is only for 50 hertz. Okay. So you should be careful here. It is a frequency dependent system. So F into L, we have to consider F into L. If F into L is less than 4,000, then it is a short transmission line. Okay. Then F into L is greater than 4,000 and less than 10,000 or 12,500. We consider it as medium transmission line. If it is greater than 12,500, we consider it as long transmission line. Okay. So this is the most important part you should remember. Okay. So this 80, 200 or 250 or 250 are basically frequency dependent, and these are for 50 hertz. Okay. I hope you understood the thing. Okay. So you can just write down this, then we can move to the next session. Okay, so okay, so you can just write down all these things, and I will go to the like short and medium transmission. We will discuss more about short, medium, and long transmission. Okay, so first we will look at short transmission. Or like you can wait for some time so that the other slides will get saved. Okay. Short transmission line. Okay. So what it is basically L and R and L. Okay. So the important property of short transmission line is the distance length should be greater than 80 kilometers. Okay. And second property is that this is a lumped system. Okay. Meaning of lumped system is that the total resistance for 80 kilometer is lumped in R. Okay. So what is the resistance of the line for the 80 kilometer? So that much kilometer is actually lumped in R. And the total inductance for 80 kilometer is lumped in L. Okay. So what is the total inductance there? That is actually lumped in L. Okay. This is basically known as the thing. Okay. So this is V in input voltage, or this is the V out. Okay. Another way we can say this is the sending end voltage. This is the receiving end. Okay. So this is the thing. So if I write, we can write V receiving is equal to, these are vector phases. Okay. V sending plus I angle some -5 we can take, like the load is actually lagging if you take, into R plus J XL. Right. This will be the network equation for a lagging power factor condition. Or we can write if Z equal to R plus JXL, if Z equal to R plus JXL, we can write V receiving is equal to V sending plus I into Z. Right. So this is a simple equation. This is almost similar to a something known as a transmission line model of a transformer winding. So if you study the machines, there is something known as a transmission line model of transformer winding. So this is some almost similar to the equation is almost similar to that. So we can write like this. Okay, we can draw the phasor diagram. So drawing phasor diagram is very important if you go for the interviews like BARC and Power Grid. They will ask you to draw the phasor diagrams. Okay, I can draw a phasor diagram next slide. Draw a phasor diagram here. So we can write the equations again. Vs equal to Vr plus V receiving equal to V sending plus J into, we can write Ia, there will be some angle, to Ra plus Jx, or like we can write Ra plus Jxl. So these are just numbers. So we can take Vs. So this is V sending. Okay. So we can take V receiving end voltage here and assume that this current is actually lagging with some power factor 5. This depends on the load. So what is, if the inductive load is connected on transmission line, then the 5 will be actually negative, lagging the voltage. If some kind like very high leading load is connected on the transmission line, then the actually current will actually leading, like that. Okay. Now we can add I is this way, so IARA is coming this way is parallel to IA, and perpendicular to this will be IA into axis, and this will be the sending. Okay. This will be the phasor diagram for a short transmission line. This will be phasor diagram for a short transmission line. Okay. So we can write all these things. So this will be IA into ZS. Okay. So you have to draw all these. They ask you draw the phasor diagram of a short transmission line. You have to draw all these things. Okay. So like these are very simple things only. If you study the phasor diagram of a transformer winding, then you can easily draw the phasor diagram for this particular transmission line also. Okay. This is basically for a short transmission line. Now we can think about what is the transmission line parameters. This is very important. Transmission line parameter. So that can be written as this is similar to ABCD parameter. Okay, VS IS equal to we can write ABCD into VR IR. So V sending and V receiving in terms of V receiving and I receiving. Okay. So if you consider the ABCD parameter of this one, assume that the impedance of this is Z. So where is Z equal to R plus JXL. Then we can write the transmission line parameters as VS IS is equal to 1 Z 0 1, right, into VR IR. Right. So you can actually derive this you just study this. This is the most important part. So VS IS equal to 1 Z 0 1 to VR IR. So assume that if it is a shunt one, okay, having a conductance Y or it can say admittance Y, then we can write VS IS will be equal to 1 0 Y 1, okay, into VR IS. Okay. So you should remember this. If it was a series like this, then it will be VS IS equal to 1 Z 0 1 into VR IR. If it is something like a parallel like this, it is happening to be something like parallel or actually opposite of this one, then we can write VSI is equal to 1 0 y. So just mug up this because we will be using this one for actually deriving the ABCD parameters of medium and short medium transmission lines. So medium transmission line will be cascading effect of these three ones. Okay, so we just find individually, then multiply everything together. So we will get a you will get the ABCD parameter for medium transmission line. Okay, so this is very important. You can actually write all these things. This is very simple, and you can do. I wait for a few minutes so that you can actually write all these things. Okay. Okay. Then now we can go to medium transmission. Okay. Now, if you go to medium transmission line, I have already explained that medium transmission line will be actually the length will be greater than 80 kilometer and less than 200 kilometer or 250. These are two standards. Okay, you can use either 200 or 250. and here also there will be lump parameter. Okay, so there are actually two representations for this. So here you have to consider lump R, L, and C. C is the capacitance of the transmission line. Capacitance of the transmission line. Okay, so we have to consider R, L, and C. So I think you understood this. Now actually we can look at the media transmission line. So there are actually two types of media transmission line. There are two ways of representing this. First one is the nominal T method. You should remember this. In this two, R and L will be something like a series. Okay, and C will be parallel. Okay, because that is a normal way of representing R, L, and C. Okay, so R and L will be in series, and R and L will be in series, and that is basically Z. And C will be parallel, that is Y. Okay, so this is important. The nominal T method we can write like this. Okay, this is a nominal T. So this will be Z by 2, Z by 2, and this will be Y. Okay, so this is basically known as the nominal T method. So now we can check how many nodes are there. This is one node is here, one node is here, one node is here, and one node is here. Okay. So there are actually 4 nodes in nominal T methods. Assume that there are actually something like 1,000 or 10,000 nodes, transmission lines are there. Then how many nodes will be there? So 4 into n number of nodes will be there. Okay. This is very important actually, because if you use transmission line for solving some kind of a power flow or something, then we have to solve for all these voltages. Okay. So that is the important part. Now we can write the ABCD parameters. Okay. So I already explained that for finding the ABCD parameter, we have to find the ABCD parameter of this. So we already know, right? 1 is Z by 2, 0, 1. Then multiply that with this. So this will be 1, 0, y, 1. Then multiply with this. So this will be again 1 is Z by 2, 0, 1. Right. So these are the 3 subsystems where we have to actually multiply. Okay. So if you multiply these 3, you will get 1 plus Zy by 2 Z into 1 plus YZ by 4, then Y 1 plus YZ by 2. So this is the ABCD parameters. Okay, so you should remember this. This is basically the ABCD parameter. Okay, now we can check whether your derivation is correct. Then AD minus BC, if you make it, will be 1. Okay, so if you multiply A into D minus B into C, you will get 1. Okay, so that is one of the important property of a transmission parameter. Okay, AD minus BC will be 1. Now now we can look at this is basically nominal T method. Okay, nominal T method of representing. Okay. So this Z is basically, if you like Z will be R plus J omega L, and Y will be 1 by J omega C. So this is important. You should remember this. Z equal to R plus J omega L and Y equal to 1 by J omega C. Okay. Now please write this one, so we can move to the next part. Okay. Now we can look at the nominal pi method. Nominal pi representation. Okay. So if you look at the nominal pi representation, what we are doing is it is like this. It's similar to a pi. This is basically Z, and this is y by 2 and y. Now we can check the number of nodes. Okay, this is one node, this is one node, and this is one node total. So that means here we have only 3 nodes. So in your interview, they might ask, what is the advantage of representing a transmission line as a nominal pi method instead of nominal t method? Then the advantage is that if you represent it as a nominal pi or nominal delta, it is also known as nominal delta. Because if you look at this, it's almost similar to a delta, okay, close to one. So nominal delta. So advantage of nominal delta is that the total number of nodes are basically 3n only. We don't want to consider 4n nodes if there are n transmission lines. Okay. So there in nominal t method, we have to consider n, 4n nodes or like not 3n. Yeah, here it will be 4n for nominal pi method. Sorry, nominal t method. So nominal t or nominal star, which is also known as nominal star. So if you just move it here, then it will be t. Okay. So nominal star or nominal delta, the important thing with delta is that there are only 3 nodes for one delta representation. So where this is advantage is that here we have to find only 3n variables, right? 3n voltages. Here we have to find 4n voltages. That means number of equations or number of the the solutions of linear equation. We have to find only 1n less number of solutions. That is the important part. Okay. So we can find the ABCD parameters. Okay. Of this. So you write the ABCD parameter and take the ABCD parameter of this, that is 1, 0, 5 by 2, 1. And here it will be 1 Z 0, 1. Here it will be 1, 0, y by 2, 1. We multiply these 3, we will get the values. Okay. We will get the ABCD parameters as and right here 1 plus YZ by 2 Z y into 1 plus YZ by 4 and 1 plus YZ by 2. Okay. Here also if you check AD minus BC will be equal to 1. So that is another thing we can actually check. Okay. This is basically nominal pi representation. Okay. So next one is so I hope you understood, and I'll give you some 1 or 2 minutes so that you can write all these things, and they might ask you to derive all these things. So don't mug up the derivation. Okay, just do this. You'll get this value. Okay. So you can actually save all these things and you can just do it. Okay, that is the most important part. You can just mug up this, how to write. I will explain again. If it is a series element, it will be 1 plus 1 Z 0. It is a parallel element 1 0 5 1. Just remember these. Okay, the rest of the things it automatically follows. You don't have to worry about it. Okay, so we can write all these things and we can start. Now we can check a long transmission. So what is basically long transmission line? So in long transmission line, the length is actually greater than 200 kilometer or 250 kilometer, right? And here L, R, C is distributed. So distributed in the sense is that like these are actually distributed throughout the length. Distributed. I think. So these are distributed throughout the length. What is happening? Distributed. Distributed parameter model. Okay. So that means here okay. Here R, L, C is distributed. In the sense, if you represent this as a circuit, we will get a differential equations. This is the most important part. We will get differential equation. Instead of linear equations, in the case of a lump system, here we will get a differential equation. So if you check here, I will give you one example. So this is the equivalent circuit for a distributed system. So you can think about like these are the cell inductance and these are the capacitors. So this will be L delta X, L delta X, L delta X, then CG delta X, CG delta X, CG delta X. And the important thing is that why there is no mutual inductance in transmission line. Because we are only considering self-inductance, right? Why there is no mutual inductance? in transmission line? Again, this is a very good question. Many people ask you in a interview, right? How can you explain to that? Because there are actually different sections of transmission lines are there. Why there is no mutual inductance? Only there is self inductance, right? So what is the problem with the mutual inductance? So if you look at the transmission line, right? So assume a small section here, okay, which I have drawn here. It's a small section. If I draw here that small section, so the current is actually flowing through the lens. So the magnetic field will be around this, right? Like this. So this magnetic field due to this small section does not meet the other sections, right? Now take a second section here. So its magnetic flux will be actually like this, right? It does not meet this one. So everything will be like this. So if you draw it, like first off it will be like this, second it will be like this, third it will be like this, fourth it will be like this, fifth. That means there is no sharing of flux, right? There is no sharing of flux happening, right? So that means there is no mutual inductance. Since there is no sharing of flux, because flux due to this small element is concentrated only on that element, right? Like this. It is not touching the other element. So other element will be like this. So it is this that does not touch here. So that means there is no mutual inductance. So if you consider transformer winding, okay, something like this. So the flux due to this will be like this. So that will touch all other windings, right? So this also it will touch here. This also it will touch here. Similarly here also, this will be like this, right? So that's why we have to consider mutual inductance in transmission line. Sorry, transformer winding. And we can avoid mutual inductance in transmission lines. Okay, so this is the most important part. Okay, like you should explain these things to different people. Okay, well, while they ask your question, why you are actually considering like mutual inductance in transmission line, transformer winding, and not in transmission line. Okay, these are the important questions you should actually think about. Okay, so that you can get this. So now we can write the governing equation for the system. If I draw it again, L delta x, L delta x, Cg delta x. Here also. Cg delta x. And here also Cg delta. Okay. So now we can take a current like this. Okay. I, then it will be I minus delta I, right? Because delta I current is actually flowing here. So that current is this, assume that this is something like V. So this is something like V minus delta. Delta V voltage is actually happening. Okay, here also there will be something like delta V. Okay. So this will be a normal current. So this delta I current is actually flowing through this delta X, right? So delta I equal to Cg delta X into dou V by 30. Right? I equal to C dV by dt. That means, so you can take minus because current is actually flowing from this direction to this direction. It's flowing from this direction. So there will be loss in current. That means dou I by dou X equal to minus Cg into dou V by 30. Right. Similarly, if you write the voltage here, delta V equal to L delta X into dou I by 30. Right. So that means minus V equal to minus L into dA by dt. So dou V by dou X equal to L minus L into dou I by dou t. Now we differentiate this with respect to because here dou I by dou t, here I dou I by dou X. So with respect to t here, so that is dou I by dou square I by dou X dot, right, equal to minus Cg into dou square V by dou t square. So here we will actually differentiate this with respect to X here. So dou V by dou square V by dou X square equal to minus L into dou square I by dou t square. Sorry, dou square I by dou X dot. So these are actually same, and then we can actually substitute it here. So what we will get is dou square V by dou X square equal to 1 by LCG. Sorry, dou square V by dou X square equal to LCG dou square V by dou t. Right. So this will be the equation. So if you write like this, so we know that 1 by root of LCG is basically V, right? So if you cross multiply this, 1 by V square equal to LCG. That means dou square V by dou X square equal to 1 by V square dou square V by dou t square. Okay. So this is similar to a wave equation. That means in a transmission line, the electrical and magnetic energy is flow as a wave with a speed equal to v. Okay. So if it is happening in a something like thin air or something like a vacuum, that will move in 300 raised to 8. Okay. So that is basically normally if it is happening through air, then it is the velocity of this is basically 300 raised to 8. And we can check here. So just check a dimension here. Okay. So this is x. X is the distance. Distance will be equal to velocity. So distance square, right? So square will be equal to velocity square into time square. Okay. So the dimension is also correct. And now we can actually find the equation using something like a standing wave solution. We can find traveling wave solution. We can find. Now these are actually some higher level things. These things actually you will study in your masters. What is basically standing wave solution for this equation? And heat and wave equation is actually very famous. I think you have studied in your engineering mathematics also, right? So you can actually look at all these things. Okay, fine. So this will be standing wave solution. Okay, you can find a standing wave solution for this, and you can find a traveling wave solution. So general solution will be something like f of x minus t by v. This will be a general solution. Okay. Something like this we will get. Sorry, t minus x by v. F of t minus x by v. That is dimension correct. Okay. Time and x by velocity by distance. So like this, you can find a general solution. Okay, these are actually higher level differential equations, you don't worry about it. Just study how to derive this equation and why this is known as a wave equation, because this is similar to a wave equation. What we see in normal electromagnetic waves. Okay, so that's why if this is also similar to the wave equation, what is Maxwell's kind of a wave equation? Del square V equal to 1 by root V epsilon del square V, but like that kind of equation also we can derive from this. Okay, so this is basically your distributed system. Okay, you can write all these things and you can actually write all these things. So this will be helpful for your interview. So if they ask derive the wave equation for a transmission line, you can just directly derive all these equations. Okay, so they may ask why are you putting minus here? Minus here is because this is the direction of flow. Okay, because as x increases, flow decreases. So in some old textbooks, we can see the flow direction of flow like this. This is basically x equal to 0 and basically x equal to 0 and x equal to n. This is the starting place. So as the x increases, flow also increases. So then at that position, we don't want to put this negative. So if you take x equal to 0 here, x equal to L here, and flow is actually this side, then we have to put this minus everywhere. Okay. So like this is a simple thing, you can actually look at this. So these kind of questions they might ask, because why are you putting this minus? So that will give you a grip on your subject. Okay, that is the most important part. You have to look at all these things. Okay, so by this we are ending this session. In the next session, we will be actually studying this how to find L, C, G, R. Okay, different inductance, capacitance for different transmission line. How are you finding all this? Because in this equation we are actually writing L, C, G, and R, right? So in this session, in the next session, we will be actually finding how to find this L, C, G, and R. Okay. Okay, so by this we are actually ending this session. Next session we can find the analytical expressions for inductance, capacitance, and resistance. Okay, thank you. So we can meet in the next session.